Okay, so here we go for chapter 2, section 4. This is the last section of chapter 2. So in 2.4, we're going to cover scatter plots, correlations, and regressions. Some key concepts we'll cover here in 2.4. We're going to introduce the analysis of paired sample data, and we'll define what that means within this lecture. We'll also discuss correlation and the role of a graph called a scatter plot, and provide an introduction to the use of a linear correlation coefficient, and we'll define all of these concepts. The last part of this section will provide a very brief discussion on linear regression, which involves the equation and graph of a straight line that best fits the sample data. So you might have seen the line equation of y equals mx plus b. We'll use that line equation when we're discussing linear regressions at the end of this lecture. Okay, so to start out here, scatter plots and correlations. Correlation, these exist between two variables when the values of one variable are somehow associated with the values of the other variable. And we'll get into an example of this. Similarly, there's a type of correlation that's considered a linear correlation. This exists between two variables when there's a correlation and the plotted points of the paired data result in a pattern that can be approximated by an actual straight line. Okay, and we'll go into examples of all of this. Okay, the next big definition here is to define a scatter plot. A scatter plot or a scatter diagram is a plot of paired or XY quantitative data with a horizontal x-axis and a vertical y-axis. This is where the horizontal axis is used for the first variable, or x. So here's our x-axis going horizontally. And the vertical axis is used for the second variable, y. And here's our vertical axis, y. So for scatter plots, it's important to know that usually we'll only need the first quadrant here. And this is highlighted in yellow. This is the first quadrant of your graph. There is an example scatter plot for you to practice making, and that's in your student outline for 2.4. Now let's look at an example of a correlation. Here on our x-axis, we have waist circumference in centimeters. On the y-axis, the vertical axis, we have arm circumference in centimeters. Now remember, a correlation is the distinct pattern of the plotted points when they suggest there's a correlation between the waist circumferences, or our x variables, and arm circumferences, our y variables. Now visually here, we can sort of tell there is a correlation, and we'll get into mathematically, statistically, how we can actually prove there's a correlation numerically. Now here's an example of no correlation. On the x-axis, we have weight in kilograms. On the y-axis, we have pulse rates in beats per minute. So here for this data, we took the weights of people, we have our pulse rates, and we're seeing if there is a correlation between the weight and the pulse rate. When there's no correlation, the plotted points do not show a distinct pattern. So it appears there is no correlation here between weights, our x variables, and pulse rates, our y variables. And again, so far, this is all just telling more visually, where in this example, where there's no correlation, we don't see sort of a linear pattern of data, right? So the data points are sort of scattered throughout. Whereas going back to this example real quickly, there is a linear correlation here, at least we can see visually. Okay, now, so I mentioned there's a way mathematically to tell if there is a linear correlation or if there is a correlation. This is where we get the concept of R, which is our linear correlation coefficient value. This linear correlation coefficient value, denoted by lowercase r, it measures the strength of the linear association between the two variables. Now let's remember here what the two variables are. For the graph on the left, one variable is waist circumference in centimeters, the other variable is arm circumference. Now the two variables here on the graph on the right, we have weight in kilograms as our first variable. As our second variable, we have pulse rate. So if we can obtain R, which is the linear correlation coefficient, we can tell numerically, in addition to visually, if there is truly a correlation between our two variables here. Okay, so now once we obtain an R value, a linear correlation coefficient, it's always going to be between -1 and +1. Now, importantly, if R is close to -1 or close to +1, there does appear to be a correlation. And if you're wondering how we define close, we'll talk about that in this lecture. Now, if R is close to the value of 0, there does not appear to be a correlation. Okay, and so hopefully you all have downloaded Microsoft Excel at this point. And what's really nice about Microsoft Excel is that you can compute the correlation coefficient R when you have a set of data in Excel. So we'll start working with Excel pretty shortly here because it is a really, really useful tool in statistics. Okay, let's look at this example here. So here we have one variable, shoe print length in centimeters. Our other variable is height in centimeters. Shoe print length is the X variable, it's on the X axis. Height in centimeters is our Y variable, it's on the Y axis. So here we have 5 different people, I'm assuming they're people, where we have a shoe print length of 29.7 centimeters. This data point is from this person who has a height of 175.3 centimeters. This is also why we call the concept paired sample data. So one pair is one shoe print length paired with that specific height. So the pair comes from one person or one source. Okay, so by collecting this data and plotting this data in a scatter plot, we can start to tell if there's a correlation between our two variables being shoe print length and height. Now recall, once we get our value of R, if R is close to -1 or close to +1, there appears to be a correlation. If R is close to 0, there does not appear to be a correlation. So again, because of how handy Excel is, we can get a correlation value. We can get our lowercase r value here with Excel. For the example on the last slide, that R correlation value is 0.59. Now, do we think 0.59 is close to 0 or is it close to +1? Well, it's pretty difficult to tell here from this R value. It's not very clear whether there is a correlation or not because 0.59, it could technically be rounded up to 1, but again, it's very difficult to tell if this is closer to 0 or closer to 1. To say with more certainty, this value of 0.99, we could definitely say that is close to 1, but a value like 0.59, we can't say that's that close to 1. So in cases like this, we introduce the concept of a p-value. So with the p-value, if there really is no linear correlation between the two variables, i.e. when r is close to 0, or it's some in-between number between 0 and 1 and 0 and -1, when we're not really certain whether there is a correlation, it's a good idea to also calculate our p-value, and then we have a better idea of whether there is a correlation or not. So what is a p-value? A p-value is the probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. Now let's break this down a little bit. So let's define paired sample data. So example of paired sample data is where each data point in one data set, here for example shoe print length, is related to only one data point in the other data set. So here height. So again, 29.7, this is related to only one other data point in the data set, which is 175.3 centimeters. Okay, let's talk more about p-values here. So from our last example, we saw an R value of 0.59. Now recall, we couldn't really say with certainty whether there is a correlation or not with that sort of R value. So what does more extreme mean? More extreme would mean closer to 1 or closer to -1 than -0.59 is. And the reason here I'm bringing up -0.59 is if we had a negative slope and that negative slope was close to -1, this also means we likely have a correlation. So our slopes won't always be positive 0.59 where they'll be close to the value of 1. They could also be a negative slope, and then we'd look for an R value close to -1. Essentially, why we calculate a p-value is to tell us whether we do actually have a linear correlation between the two variables. Let's now go through an example to hopefully solidify this more. Now recall from chapter 1, statistical significance is achieved in a study if the likelihood of an event occurring by chance is only 5% or less. If the likelihood of an event occurring is by chance, then we don't have statistical significance. Right, so it's this balance between could this just happen by chance or is this statistically significant? So how do we interpret a p-value? Only a small p-value, such as 0.05 or less, which is the same as a 5% chance or less, suggests that the sample results are not likely to occur by chance when there is no linear correlation. So a small p-value supports a conclusion that there is actually a linear correlation between the two variables. So again, the first step here is to calculate an R value. If we get an R value that's exactly 0 or pretty much exactly 1 or -1, then we're certain that there is no correlation if it's 0, or there is a correlation if it's -1 or +1. If it's a value that's somewhat in the middle, we should also calculate a p-value. So once we calculate that p-value, if we have a small p-value, it supports a conclusion that there is actually a linear correlation between the two variables, even if our R value did not suggest that as strongly, okay? Now let's look at an example, and we'll also discuss p-values more in Chapter 8. The goal here for p-values is to introduce you to the concept and understand why we calculate both an R value and a p-value, and what the different p-values and R values mean. Let's go through this example now. So from Excel, also really useful, we can calculate a p-value. The p-value here is 0.294. This is considered a high p-value because it's much greater than 0.05, right? So recall from the last slide, a small p-value of 0.05 or less suggests the sample results are not likely to occur by chance when there is no correlation that we saw from the R value. And also remember, if a situation is not likely to occur by chance, then the opposite of something occurring by chance is that we have statistical significance. But remember, for this example here, we have a p-value of 0.294. So we don't have this situation here in this other bullet point. Rather, this p-value shows there is a high chance of getting a linear correlation coefficient of R equal to 0.591, or more extreme, so closer to the value of 1, by chance when there is no linear correlation between the two variables. So overall here, we have an R value equal to 0.591 for our data set of shoe prints and heights. But this p-value, that's pretty high, that's telling us that there was a high chance of getting a linear correlation coefficient when there really is no correlation between the two variables. Okay, so again, we're sort of on the fence here with 0.591. When we get the p-value, this proves to us that there was a high chance of getting a linear correlation coefficient just simply by chance, rather than there truly being statistical significance. So what do we conclude here? Here we say there is no correlation between the variables x and y. Why? We had an R value of 0.591. We were sort of on the fence with that one. We went and obtained a p-value, which you can do in Excel. Our p-value was very high, so from that data point, we can conclude there is no correlation between the variables x and y. Another piece of data I'll point out right here is our sample size of n. Our sample size of n was only equal to 5 in this case. In a few slides, we'll go through an example where n is equal to 40. Okay, so again, here we conclude there is no correlation between the variables x and y. So to put this in other words again, now because the likelihood of getting R is equal to 0.591, or even a more extreme value, such as 1, is so high, because we determined our p-value is 0.29369. If we convert that into a percentage, what that's really telling us is we have a 29.4% chance of obtaining this R value, or even one higher, just simply by chance and not by true statistical significance. So we conclude there is not sufficient evidence to point to a linear correlation between shoe print lengths and heights. Okay, so what I highly recommend you doing in your student outline is to note when we have a certain R value between -1 and 1, what it means if we have an R value of -1, 0, 1, or somewhere in between. Then in addition to that, when we get a p-value, I want you to clearly write out what it means as far as can we conclude if there's a linear correlation or not based on the p-value that we get from that same set of data. So far we've gotten a pretty high p-value of 0.294. Now we'll also talk about the other case where we have an ambiguous R value, but we have a very low p-value and what that means. And now again, I pointed out that n was equal to 5 for that previous example. It's because we had 5 pairs of data. And n represents the number of subjects or the number of data points or pairs. So here for this example, we have n equal to 5 because here is 1, 2, 3, 4, 5 pairs of data. Now, in the realm of statistics, having only 5 pairs of data, that's not a lot of data to go based off of. Next, we'll look at a study of the same 2 variables, so shoe print length and height, that contains more data. So we have n equal to 40 for the next example. So now n is equal to 40, so we have 40 data points here, where our x value is still shoe print length and our y value is still height in centimeters. Now just visually, again, we can look at this data. The scatter plot does appear to show a pretty distinct pattern. It does look linear. Now let's go into mathematically how we can prove it or disprove that there is a correlation. Now this is another example of data we can get using Excel. So here the correlation matrix displays an R value of 0.813. Now that's a little bit less ambiguous, that's a little bit closer to 1. So we're probably more likely to think there is a correlation here given that R value. Now again, we can always calculate a p-value to even tell us with more certainty whether there is a correlation or there's not. And recall, when R is close to -1 or +1, there appears to be a linear correlation, but we can also use a p-value. So the p-value here is also shown, where this p-value is calculated to be less than 0.0001. And now this quote was on a previous slide, but I'm including it here again, so we can make a conclusion based on that p-value. Here, because the p-value is very small, it's less than 0.05, we have sufficient evidence now to conclude there is a linear correlation between shoe print lengths and heights. Okay, so again, in the exercise I previously mentioned, I want you to write out clearly for yourself what different R values mean, and now here what different P values mean. Write out clearly what it means if a P value is greater than 0.05 or if it's less than 0.05. And now here, this example where we had n equal to 40, we had a very small p-value. So from this data, from these p and r values, we can conclude there is a linear correlation between shoe print lengths and heights. Now remember this difference here. In the last example, n was equal to 5. That's not really that many data points to go off of. Here, n is equal to 40. So we had more data points to go off of, and we actually got a different conclusion. The conclusion that is more trustworthy here is the one that came from a data set with more data points, so n equal to 40. So in statistics, you usually want to accumulate as many data points as you can. That makes sense with the amount of time that you have to spend on that project. Okay, the last bit of 2.4 is talking about regression. So given a collection of paired sample data, the regression line, or line of best fit, or least squares line, you could hear them called either one of these, is the straight line that best fits the scatter plot of the data. The regression line equation I mentioned at the beginning, you might have heard of y equals mx plus b. This is really similar here. It's essentially the same thing, where the regression equation is y hat is equal to b naught plus b1 times x. Now, if you're used to seeing a line equation as y equal mx plus b, where m is the slope and b is the y-intercept, this is the same thing, but in this case, b1 is our slope because it's next to x, our x variable, and b naught here is the y-intercept. Okay, so this is the same thing as thinking of y equals mx plus b. Now, previously we had a scatter plot. Now on this graph, we've actually added this line here, this regression line, this line of best fit, or in other words, this least squares line. Now again, using Excel, which is super handy with statistics, we can calculate the equation of that line. So this is what we'd get in Excel. And from that, we know the equation for the regression line is y hat, or y equal to 80.9. So that's our y-intercept, plus 3.22. That's our slope rounded up, multiplied by x, which is our x variable, which in this case is shoe print length. Using actual variable names here, y is the height. So height is equal to 80.9, our y-intercept, plus the slope, 3.22, multiplied by our x variable, which is shoe print length. And again, this is because height is our set of y variables and shoe print length is the set of x variables. From the general form of the regression equation, we can actually write these numbers out. So the y-intercept of b naught is equal to 80.9. The slope, b1, is equal to 3.22. Okay, and that is actually the end of 2.4. Remember what I said about writing out really nicely what different values of R mean and what different p-values mean. So be sure you do that. And if you do not have Excel downloaded at this point, make sure you get that downloaded. And as always, let me know if you have any questions at all, especially related to the homework. Stay safe and healthy this week, and I'll talk to you all soon.